All right, let me just remind myself where we left off, because I want to start talking about threads, but I have to decide whether I want to start that in a new project or continue with our current project. So give me a moment as we talk about interfaces. We did merge sort. Okay. Yeah, let's start this in a new project then, because we're kind of past our searching, sorting stuff, and we can move into some other things using more complex inheritance models like abstract classes. So let me go ahead and create a repository. And we're going to call this guy CSC250. I'm just going to call it threads for right now. All right, and I'll go into Eclipse. And let's create a new project. And we're going to call this guy CSC250 underscore threads, but we're going to store it in our repos directory. And then don't create my module. And I'll go ahead and create my driver. I'll go ahead and have it generate main for me. I think I've told you that before, that you can click this button and it'll go ahead and generate main. Only do that once you're very comfortable writing this multiple times, because I think having the stub of a basic program in many languages is very beneficial. So you can just sit down and start working in that language. All right, we have a running program now. All right, so last time we started talking about, well, I think I kind of introduced the idea of multiprocessing inside of our computer, where, and let me draw a little picture, because I mentioned a couple of things that maybe I took for granted a little bit. So let me do this. So when we talk about CPUs, we used to have single core CPUs. Then we had dual core, then quad core. You know, now you have some that are like octa-core or 6-core, and even at Intel, they have some experimental things that are even larger than that. Well, the i9 has a 32-core that's really expensive. So, but multiple cores is the lesson here, right? Having more than one core. So now, but before we had dual core, we had dual CPU machines. Physically had two processors. Okay, so if you opened up the computer, you would see two physical processors inside the computer. In fact, we moved the machine out, but we have a dual processor machine back there, our render machine. It was right next to the right of the door back there. Our render machine for the graphics classes has two CPUs in it, and each one of those CPUs has 48 threads. It's a 48 thread CPU, so it's a total of 96 threads across two CPUs in that computer, which is pretty, or 96 cores rather, across two CPUs. All right, so before we were able to do multiple core CPUs, we had dual CPU machines. So it was two single core in a single computer, giving us two two simultaneous processors. Now, what does all this mean? We can say that each core can accomplish a single task at a time, which means that if I have two physical processors, I have two cores, I can technically do two things at once. If I have a dual core processor, I have two cores, I can technically do two things at once. Quad core can technically do four things at once, so on and so forth. All right, so quick question is, are more cores better? Is a 32 core processor better than a quad core processor? As you might guess, the answer is it depends. So if you are performing a task that can be divided up into several smaller tasks, sure, the more cores, the better. So let's use this example. Let's say that, okay, so we're in the fall, there's leaves all over the place, right? And let's say that I can rake leaves at a speed of 10 individually. And let's say all of you can rake leaves at a speed of 6. Now, I'm much faster at raking leaves than you are as individuals. But who's going to be able to rake all the leaves around campus quicker? Me or all of you working together, where you take different parts of campus and rake leaves in the different parts of campus? Probably the group of multiple people raking leaves, right? Unless you were so slow that I could play catch up, right? Okay, so in problems, when we're solving problems that can be broken down into subdivided tasks, like we didn't have to rake the leaves outside of the field house before we rake the leaves by the bluff. Those two things could happen at the same time, right? So if I had two different people raking leaves at the same time, that would likely be faster than a single person who's a little bit quicker at raking leaves doing one of those and then the other one. Make sense? So that's where it depends. If you are working with different processing, that you know the kinds of problems you're solving are divisible problems. So that's why I mentioned earlier we have our rendering machine for doing 3D rendering and animation stuff. You know, that is a task that can be done in parallel, where we can render parts of an image or parts of a video and have each of those cores working on part of it. So they all can accomplish the thing much, much, much faster because you have more of them working on it simultaneously. Whereas if we look at it from like the video game perspective, fairly often, even though there is some advantages of having maybe a dual or a quad core for video games, but maybe in the early days, this is the better explanation. When asked, would you rather have one really, really, really fast core or two slightly slower cores for playing a video game, you'd rather have one really, really fast core. Because usually you have a single CPU that's almost maxed out, working about 100% of the time when you are playing a game, because games, a lot of times things can't necessarily happen in parallel, or at least important things don't happen in parallel. You know, there might be some background chatter type stuff you can put onto a second core, but your main core is what's giving you most of your logic while you're playing your game. So it really depends on the task you're accomplishing, whether you'd prefer to have faster and fewer cores than slower and more cores. Because typically, the more cores you have, the slower the maximum speed of the processor tends to be, because then you're getting more heat involved. That's not a pure truth, but we can call that a relative truth. All right, so more cores aren't necessarily better, but right now we're trying to talk about this concept of, let's assume I have a computer program where I do want to have more than one thing happen at once, right? And initially we'll come up with a stupid little example where, like, okay, those didn't have to happen at once. We just proved we can do it. And then we'll give it a better example, okay? So we have this concept of an interface, first of all, in Java, as well as other object-oriented languages. So an interface is kind of like a class, In fact, I'll just go ahead and put this in the slide. We might bump into it here in a little bit anyways, but an interface, this guy is kind of like a class, but it does not contain an implementation. That is to say, no logic code is written, just called a skeleton framework. So what does an interface say? An interface, describes the rules that all implementing classes must follow to successfully, let's say to be compatible with an interface. And let me give you a real life example. All right, so you're in the grocery store, you're in Target or whatever, and most of the you pick up any item, you have that little code thing on it with a bunch of the vertical bars, the UPC code, right? All right. Now, how do you read those UPC codes? Like, how does that get read? Like, as humans, we don't read them. A machine reads it, right? So at Meijer, if you go through the self-checkout, you got to take the UPC code and scan it over the little laser thing, and it'll beep, and it read it, right? Similarly, the people working there might have a little UPC gun, right? That they can go and they can scan stuff. Now, do you think more than one company makes those UPC guns? Do you think more than one company makes those self-checkout machines or even the normal checkout machines? So do you think that the companies that are making the paper towels, do you think they make a different packaging for that paper towel with a different UPC code on it to be compatible with company X's UPC reader versus company Y's UPC reader versus company Z's UPC reader? Or do you think that there is a standard for what UPC looks like, and that all of those companies that make UPC readers follow that standard? That seems more likely, right? That there's this standard called UPC, and if you're somebody who's making a UPC reader, whether it's the gun kind or the checkout register kind, both of those, they have to follow the standard defined by UPC. That makes sense? Okay. So that idea of a standard is kind of like our idea of an interface, where you might have some of those scanners or some of those guns that have extra features on top of its UPC reading feature. Maybe they go back, check back to a database that, for instance, if you're in a grocery store or something like that, they might be able to scan something and then it actually shows them what the actual quantity they have in the store is, right? It's stored on top of a shelf somewhere or whatever, but they say, oh yeah, we got 30 of these, even though they only show 2 on the shelf or something. So that UPC reader, it knows how to read UPCs, but it also interfaces with, maybe their inventory system or their, something like that. And that might be more custom, that piece where you might have, okay, I'm going to buy company A's UPC gun because it also knows how to talk to the inventory system my company uses, something like that. But all of them are compatible with generic UPC codes. They can read it. So they have to have implemented 2 or 3 different, let's say, little abilities so that they can read a UPC code. That would be following an interface. So a human version of this would be following a standard. So somewhere there's written up the standard for what UPC codes are. And anybody who wants to participate with the UPC code system has to at least adhere to that standard. They want to add some extra stuff on top of that or outside of that, that's fine. But at the very least, they have to adhere to that standard. That makes sense? But that standard does not dictate how they build their UPC gun or their register. It just says, however you make it, it needs to be able to do this, 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 and this. That makes sense? You can use any sort of cool technology, lasers, whatever that you want to accomplish this task, but given this input, it has to give you this output. All right, that's kind of what an interface is. It defines how something must work, not how you have to write it. Okay, so to give you an example of one of these, we're going to look at the Runnable interface in Java. Now, one thing is almost all a naming convention for interfaces in Java. Well, actually, almost all modern object-oriented languages is almost all interfaces end in able. So we've seen this before when we tried to go write a for each loop that goes through every element of an array, and it said something like, oh, arrays are not iterable. Array lists, though, were iterable. So that means that they have the built-in functions to be compatible with the generic iterator that a for each loop creates to go through everything in a collection. So most interfaces end in the, I don't know, the subword, the phrase, able. But it's a naming convention, not a rule. Okay, so we're going to be looking at one here called Runnable. And Runnable says that we must have a method. I'm not a robot. Runnable says that we must have a method called public void run. All right, so anything that implements the Runnable interface has to have a method public void run. You can put whatever you want in that method, but if you're something that says I implement Runnable, I am effectively guaranteeing anybody who uses this object that implements Runnable, I'm guaranteeing that they will be able to call a method called run. And I'm in charge of writing it. I must implement that because interfaces themselves don't describe implementations. They describe specifications, expectations for meeting a standard. If you're going to be something that's runnable, you have to have a method called run, but you got to write it. Okay, otherwise it'll say you broke the rules. Okay, and let me just show that to you. So we'll demonstrate that here. I'm going to go ahead and create a class. I'm going to call it worker B. I think I mentioned that last time. All right. Now I'm going to say that I want my worker B to implement Runnable, like that. So when we inherit from another class, we extend that class. When we say that we're going to be compatible with an interface or more than one interface, we can say that we're also going to be iterable. All right, so notice here, if I say I want to participate in both of these interfaces, I hover over worker B, it says, there are two, let's see, worker B must implement the inherited abstract methods from iterator, and it also has to do it from Runnable. So if I take out the Runnable, see the error message saying, the worker B must implement the inherited abstract method called run. Now I can go ahead and I can hover over this, and one of the things it'll say is go ahead and add the unimplemented methods. So one thing Eclipse will do is it'll say, if I say I'm going to implement Runnable, I can use Eclipse to go ahead and add the methods that I have to implement. So right there, it says, you have to write this method called public void run. All right, you have to write this method. This override directive, this is for the Java compiler. It technically makes things compile, technically make things more efficient when you're compiling it, but it's not required. I'll leave it in there since it generated it for me. But if I were writing this myself, I probably would not put that, not because it's completely unimportant, just because historically this didn't exist. So when I wrote Java stuff, my natural go-to is not to write these extra directives. Okay, but if I put them in there for you, this is just dictating that I am overriding an abstract method that was provided to me as a requirement of the runnable interface. Okay, so if I don't have this method in here, but I've claimed that I'm implementing runnable, Java's not happy because it's saying, look, you have not implemented the method you promised you were going to implement. We made that promise when we claimed we were going to implement runnable. Okay, so we'll go ahead and write that. And now what I'm going to do here is I'm going to, just to kind of get us towards this, where we're going to be going with this stuff today. I'm going to go ahead and write my constructor for worker B. And we're going to have worker B is going to take in a string name. We're going to name our worker Bs. So we'll go ahead and have a private string name as the field that this worker B will work with. And we'll say this dot name is equal to name. All right. Now inside of run, we'll go ahead and say for int I is equal to 0. I is less than, let's say 1,000. I plus plus, and we'll go ahead and do a system.out.println. And we'll go ahead and put in our this dot name and then concatenate onto that maybe a colon with a space and then concatenate onto that I. So, it'll be like, worker B1, 0, worker B1, 1, worker B1, 2, worker B1, 3. That's kind of what we're going to have this guy output. All right, so pretty simple object here. Even if all this implement says is that we had to write this function. It doesn't tell us what we have to put in there. It just says it has to exist. Possibly if we're following a standard, like I used the example of the UPC, the method might have to exist and it might have to take in a certain input and it is expected to give you a certain output. Okay, so we need to kind of follow the standard, but for this one, since it takes no parameters and doesn't return anything, it's just saying, look, you want to be runnable, you got to have a method called run. Done. That's it. That's the full rules it gives you. All right, so now I've successfully implemented this interface. I claimed I was going to implement it here, and then I followed that claim up by implementing that method. And then for my little generic class here, I'm just going to keep track of a worker B's name. So that's all I did here. And now I'm guaranteed he has a method called run. So out here, I'll go ahead and I'll say worker B, WB1 is equal to a new worker B. We'll call him WB1. Similarly, we'll create a WB2 and a WB3. All right, now I know all of these guys all have a run method. So if I say WB1 run, WB2 run, WB3 run, WB1 will block WB2 from running until it's completely done. So this will be WB1 0 to 1,000, followed by WB2 0 to 1,000, followed by WB3 0 to 1,000. Okay, so as this is written right now, it's going to use a single core. All right, this is code in a row, procedural stuff like we've been writing all along. WB2.run will not even start until this guy has completely finished. So I'll go ahead and run this. And notice here that we have, all WB3s for last, then WB2s, then WB1s. Okay, so this is 100% in order, right? Everybody sees that? All right. So now we're going to say, what if I want to make these guys threads? Now, I'm going to go look up the thread class. We're going to see that the thread class in Java, it's built into Java. It implements Runnable, which means that anything that is a thread will have a run method. The default run method does nothing. Okay, and we'll see that. But threads are something that exists at the operating system level. We talked about this last time. I introduced the somewhat humorous vocabulary for multiprocessing, the predecessor to threads, where we created multiple processes using the fork system call, but they were considered heavyweight processes in that you were actually creating a complete clone of the current program, you know, with all of its heavyweight logic, even if you were only going to do a little part of it. Where a thread, what it does is it creates a kind of a micro clone, if you will, but it doesn't get any extra CPU time. So my program here, the main thread of execution for driver, is automatically created for me. That guy gets some amount of CPU time. If he creates 3 threads, those 3 threads share the CPU time that was allotted to their parent process. So they don't get any extra time on the CPU, but they can all do the same. They can all get some time on the CPU that's interchanged with other threads that are working. So we can have more than one thing at least seemingly happening at the same time. And if you have a multi-core setup, your operating system will schedule threads on multiple CPUs. So in that case, even if you have 2 threads from one process that are both sharing the amount of time that that process gets on the CPU, technically those 2 threads could be running completely simultaneously on different cores of different physical cores of the CPU. So you could have more than one thing happening at once. You could have a number of things happening at once equal to the number of cores that you have. There's a little bit of stretch behind that where you have something with Intel called hyperthreading, where if you have a quad core Intel processor, they'll say it has 8 logical cores, because you can sort of kind of do an extra thing per core with their hyperthreading. It's something you'll learn about in the 325 class called pipelining. The way you set up instructions to the CPU, you can expedite how quickly an instruction leaves the CPU and the next one gets into the CPU using this concept of hyperthreading. So it really doesn't give you double the speed, but it makes things a little bit quicker, so you're getting some more efficiency out of that each single core. Unimportant for us in here. This is more just talking about the kind of the grand ideas of computer science, where all these things are interconnected. So in here, we're going to experience the use of threads, appreciating what they're actually doing behind the scenes, but that's not our focus in this class. The operating systems class, you'll focus on, what actually is a thread or is a process, and how does the operating system schedule those things? In the 325 class, you'll learn about pipelining as single assembly language instructions are fed to the CPU. How do they get staged so that the CPU can process the next one? As we think of the CPU as kind of like eating low-level languages. One instruction followed by another instruction, followed by another instruction. One magic trick, followed by another magic trick, followed by another magic trick, as I describe CPUs as being this collection of magic tricks. And if we can make sure that the CPU's mouth is always full, right, that there's not like downtime between letting one process leave the CPU and another one get onto the CPU, if we can make sure that it's busy as close to 100% of the time as possible through this concept, this generic concept of pipelining, that's good for us from a speed perspective. But in this class, we just care about what is a thread and how do I write the code for it. Make sense? Go ahead. Usually they're all the same, but it's actually a good question. So he asked if you have multiple cores, are they all the same or are a couple better and a couple worse? At the desktop and laptop level, modernly, most of the cores have always been the same speed. It's switching over a little bit now because over the last several years, mobile processors, and in our grad school, we have kind of a version of 325 called mobile application, mobile device architecture, where we look at the differences of architecture inside of like our smartphones. And it's become more common in our smartphones. Apple is kind of the one of the early adopters of this, where if you have one of the newer iPhones, last 3-4 years, something like that, you'll have 2 higher speed, because most of their chips are quad core. They make their own cores. They're actually supposed to have an announcement, I don't know if it's this week or next week, where they're probably going to be announcing MacBook Pros with their own silicon in them, with their own processors. So then it will be probably a reality. I suspect they would use the same kind of idea. But the idea is that for your smartphones, you know, kind of whatever application you're currently using probably needs to be fast. So you want your more powerful cores to be working on those guys. But so they're quad core processors, but 2 of the cores are much weaker. We can imagine that on our smartphone, there's probably a whole bunch of stuff going on that lower priority. We're not visually seeing it on the screen. We know it kind of needs to get done, but it could just happen in the background at a slower speed, as long as that's also saving us battery life, is the punchline there. Those 2 slower processors, slower cores, are also more power efficient. So the more things we can have run on that, the longer battery life you'll get. That's the concept behind it. So we can see that kind of going into laptop technology now, and I would predict that Apple will probably announce something like that. Because even though our laptops can be plugged in, I mean, when I'm in here, I teach for 4.5 straight hours, I plug in, but you know, pretty commonly, I don't even have a charger with me when I just take my laptop into coffee shops. So we're often using our laptops just off of battery. So we would maybe appreciate something that would give us even an extra 15, 20, 30 minutes of battery life. So that's become our new norm. So really your question speaks to kind of the current trends in computer architecture, because we are becoming less and less tethered to a wall, right? Anymore our laptops are tethered when we charge it overnight. Same thing with our smartphones. I plug mine in every night to charge up. I know some people probably just charge it every couple of days, but mine's almost dead at the end of each day. But you know, that's the punchline. So good question, and the answer is the way you were thinking is the way things are going. It's the punchline. So good thoughts. All right, so in any case, as we see right now, these things are definitely happening linearly, right? So I keep mentioning this idea of threads, but we haven't written threads yet. We haven't used threads yet. All we've done is said, hey, you know what? I want to implement the runnable interface, whatever that means. But I mentioned that threads are something that's managed at the operating system level. So from our perspective in here, we can say, well, it might be very difficult for me to implement threads myself in Java, because we're at the mercy of kind of the Java virtual machine. But whoever wrote the Java virtual machine, Sun Microsystems years ago, now it's Oracle, they had the power of implementing that virtual machine to manage threads for the underlying operating system, which was Windows, Mac, Linux, whatever it's running on. So we can just we can say that threads are kind of a magical thing that requires a negotiation between our language and the actual operating system. In Java, and even most of our modern operating systems, we don't have direct contact with the OS. That happens at the low-level line. When we looked at the Hello World program in Linux assembly, we saw it used like syswrite, talking to the actual operating system, and sysexit. So in Java, we rely on this class already existing. We have a class called thread that already exists that somehow knows how to do the magic of creating a thread. All right, so let's go and look at that thread class here. Java thread class. There's like a tree structure here you can use to search for stuff, but I always just Google it real quick, just put Java in the name of the class you're looking for, and it takes you to the right place. I think this is a little bit older. This is Java 7. There's Java 8, maybe even Java 9 now, but it's same junk. So if you're writing production code, make sure you're looking at the documentation for the correct version, but some things don't change. Like I don't think the definition of strings are going to change very often. So first of all, we notice here that the class thread implements Runnable. So this guy implements Runnable. And that means that at the very least, as we scroll down here, threads might have some other methods, but we fully expect to find a method public void run in there, right? Since it implements Runnable, it must have a method public void run. So here is our public void run right here. Okay, so it's going to have that method. Now I'm telling you the way threads work is we put inside that method the stuff that we want this thread to do. But we don't call the run method directly. Instead, we call the start method. So this causes the thread to begin execution. So basically, this lets the Java virtual machine do the magic of actually creating a real thread behind the scenes in the operating system that's being scheduled by our operating system. And that thread's job will be to execute the code that is inside of the run method that we're going to write. Make sense? That's the connection it makes. So what I'm going to do here then, go back to my code, and my worker bee, instead of this guy implementing Runnable, I'm going to say that this guy extends thread. I'm going to inherit from the thread class. But rather than using the generic run method that threads come with, that is a method that does nothing, I'm going to write my own version of public void run that's going to count between 0 and 1,000. Make sense? So looking at this in general, I really have done, it looks very, very similar to what I just had written before. The only difference is instead of implementing Runnable, I'm extending thread, or I'm telling you threads are special. There's a lot behind the scenes there, but I haven't really changed my code much, right? So now out here in driver, if I call those worker bee run methods directly, you'll see I still get them in order. All W1s, then W2s, then W3s. But if instead, since all my worker bees are actually threads, rather than directly call run, if I instead call start, which does the magic of creating that thread and then calling that run method. Okay, that's what start does. Start does the magic we can't do on our own and then calls the run method. When I run this now, we should see, notice how they're not all in order. There's a WB2, WB2, WB1, WB3. All three of those threads are working at the same time. And they're printing out their values, not necessarily in sequential order. Within each thread they are. So you'll always have 878 follow 877 from worker B2. But you actually see here, like right here, we have worker B1 just did 879, worker B2 is only on 781. And worker B3 is on 664. So now we have evidence that all three of these things are happening at relatively the same time, at the mercy of how it's actually being scheduled behind the scenes at the operating system level, whether it's running on a single core or multiple cores. We don't necessarily know. We're not promised that by Java. We're just promised that this does not block the next line. We'll add that to our notes here. Blocking versus non-blocking code. Blocking code will not allow the program to progress until that line of code completes. Non-blocking code will allow the program to progress while the current line of code is working. So what we can think of as blocking code is all the code we have done up to this point. Non-blocking code, so we can say blocking can be avoided by using threads. Does that make sense? Does that mean threads, does that mean writing non-blocking code is better than writing blocking code? Or is there a right time and place for each? Can you imagine a problem that can't be done at the same time? Where we really do need to block? If we think about this in real life, let's say you're making a lasagna. You have to get all these ingredients gathered into the pan before you start baking it, right? So we can't do the baking part and the building part, let's say, simultaneously. So the building part has to block us from doing the baking part until it's complete. We got to take all the stuff, put it in the pan, put the cheese on top, you know, all the jazz. All that has to happen in its entirety and finish before we can start baking. So those two tasks cannot be done simultaneously, right? Without severe burns, and then probably uneven cooking as well. Right? You probably don't want to put your toppings on inside the oven with it. It's a problem. All right, so that would be an example of something, of a real life task that blocking is the right way of doing it. Okay, where a little bit ago I gave the example of maybe raking the leaves around campus. That's something where we can say, hey, we can hire one person to rake the leaves and just say, hey, look, you know, go from section to section and let me know when you're done. You know, maybe it takes them 10 hours to do it. Or we can hire 4 people to do the same job where each of them handles 25% of the job. So maybe it now takes each of them 3 hours to do it. But now the entire job is done in 3 hours instead of 10 hours. That make sense? So that would be an example of a task where the second person doesn't have to wait for the first person to finish raking. They can rake by the field house at the same time as somebody else is raking by the bluff. Okay, that makes sense? So again, coding, programming mimics real life problem solving. If you can do 2 things at the same time, great, do it. If you can't, don't. Don't just create threads just to create threads because they're relatively easy to create. All right, now with that in mind, let's see, I was going to use create another example here. Oh, whatever, it'll come to me. So with this in mind, is merge sort something that can benefit from multiple threads? Remember how merge sort works. Let me go and steal my blocks here. All right, so if we have a collection that looks like that, we know that, what do? We call merge sort in this first half, and we call merge sort in the second half. Does this second half, does this guy even start the merge sort process while this guy is running? Or does my first call to merge sort, when I call merge sort on AR from 0 to 3, and then I call merge sort on AR from 4 to 7, let's say, does this second call to merge sort even begin before this guy has finished? Does not, because this line right here blocks. So however long it takes this call to merge sort, which is also, so he's going to call merge sort, which then is going to call merge sort 2 more times, which then is going to call merge sort 2 more times until they finally get down to individual, single lists. Then it's going to bounce back up and it's going to call merge on that portion of the list. Okay, so this guy has to be completely finish before this guy can even start. But if we think about how merge sort works, is it reasonable for us to sort that part of the list and this part of the list at the same time and then merge the solutions back together? That's reasonable, isn't it? Would that make things faster, especially in a situation where we have more than one core? If I have 2 cores working on this, now we're looking at kind of our example of raking, right? You're raking around campus. I got 2 people working on it instead of just 1. The 1 person took 10 hours. Maybe the 2 people will only take 6, even if they're a little slower at raking than the other person was. Okay, so now I can say, well, I want to go ahead and I want to sort the left half here, and I want to go ahead and I want to sort the right half here. And then, so what I can do is I can actually say, worker B1, you deal with this half of the list. Worker B2, you deal with the other half of the list. That makes sense? Okay. Now, I'm going to go ahead and I'm going to write another for loop here. So I'm going to say for int I is equal to 0, I is less than 10, I plus plus, system.out.println, we'll just say woot. All right, so I did that 10 times. Actually, you know what? I'm going to do it more than that just so I make sure I can see them pretty quickly. So this guy does not block, this guy does not block, this guy does not block. So all 3 of these worker bees are working in the background while this guy continues on. So I'm going to see some woots, because really this class I'm in right now is executing in what's called the main thread. So all of our programs actually already have a single thread that's been created. So my normal program is operating in the main thread. So after line 12 here, I actually have 4 threads in existence. The main thread and then 3 new threads that I've created. Okay, so all 4 of those threads are getting scheduled by the portion of the operating system that helps schedule an individual process. Okay, unimportant for us in here. All right, but the point is that none of these 3 lines block, which means that this code will be executing simultaneously to these 3 things. So I'll see woot mixed in there. Probably happened pretty early on in the, should have made it 1,000. Yeah, there was a bunch of woots and then some other woots. So you can kind of see where it got mixed in. All right, so at least evidence that it didn't block. We got that stuff in there. Okay. But now if we think about this in terms of merge sort, we might say, what if I don't want the code below to execute until all 3 threads above are done? Okay, so that's kind of what we want to accomplish here. Let me look at the chat real quick. That's true. You could preheat the oven. So that could be happening at the same time. While you're putting the ingredients, the oven could be preheating. Those could be multi-threaded. All right, so if I don't want this part of it to run until after all three of these guys are done, I have to go back and look at my thread class and say, is there a way? What kind of things can I do with threads? Is there a way for me to wait on a thread? And we have a method called join, but we'll also go and look at what else is available to us in here. So we're inside the thread class here. So we can ask, so first of all, notice here, this is a static method. So static methods are class methods. How do we call class methods? Using the name of the class in which the method was defined, right? So I can go ahead and at the very end, I'm going to go ahead and do this 1,000 times so it hopefully keeps up relatively. And then I'll do a system.out.println. Actually, I'm going to do it before that. I'll put a bunch of asterisks so I can hopefully see it. Then I'll concatenate onto that thread dot, was it thread count, current count, active count. Put some more stuff after that. So we would expect that to be 4. We have 4 active threads. I'm pretty sure thread count's going to tell us it's going to include the main thread. So we have the main thread plus the 3 threads we created. It's possible it might only say 3 for active count because it might not count the default one, but I think it will. All right, but since these 3 lines don't block, this guy's just going to be somewhere in there, right? So I'll have to go find him, and that's why I put the asterisks in there. Should be up near the top. Yep, 4 active threads. All right, so that's one ability that threads have is the thread class itself can report to me, this is through a class method, how many active threads are currently going during this during my program running here. Now, one thing I can do then, if we're asking the question, is how can I make sure that this code doesn't happen until the end? Well, one thing I can do is I can say while thread.activeCount is greater than 1, I can say basically do nothing. This is called a busy wait loop. So effectively, I'm telling the main thread to just sit there and spin as long as the active count is greater than 1. Waiting for these guys to finish, which will take the active count from 4 to 3, 3 to 2, 2 to 1. So as long as it's still greater than 1, keep doing this and do nothing. Only when that's complete can I then move on and do this stuff. So I should have woots being all the last part of my program then. That make sense? Okay, so we might call that kind of a hack. You know, this probably isn't the way. So I mean, this concept of busy wait loops, I think you've probably, I probably referenced this before a couple different occasions when it made sense with the Double Dragon game that my brother and I used to play in the arcades years ago, and we got it for PC. You heard me talk about this before? So it was a super popular game in the 80s. Oh yeah, Double Dragon was an arcade title. So this was super popular in the 80s, and then it finally came out for PC. Well, this is on floppy disk, very early PCs, right? And it ran great on the PC we had, which was this old Epson computer when Epsons used to make PCs. And years later, a couple years later, we got a much faster computer. This was during a time period where every like 6 months, computers were like doubling in speed, tripling in speed. So we got a new computer and installed this game, and it was unplayable. All the monsters all came out at once, and all this stuff, because the way they implemented the program was the time it took, like before the main boss, let's say, before he spawned and started attacking, was based on how long it took some for loop to run. It's like, well, we'll wait for it to run 10,000 times. And that'll be long enough that the player should have gotten to that guy by then, right? But what ends up happening? Well, that older computer, a for loop ran 10,000 times in maybe 45 seconds. And the newer computer, that thing ran 10,000 times in maybe 2 seconds. Bosses weren't going to wait on us. They were flooding so you had all of the guys all at once just coming at you on the screen. And then on top of that, even the animations associated with your guy moving him around the screen was all on a busy wait loop. Your guy was uncontrollable. You moved him a little bit, you just moved tons. So that kind of shows a bad programming practice, but technically, if you have a tuned piece of equipment, you can pull that off, right? And this actually isn't really dissimilar to some of the problems we have more recently solved. So how many of you in here or online are console gamers? So you play games on, PlayStation or Xbox as opposed to PC. Now you might play on both, but if you're a console gamer, this has changed a little bit now. But if we go back to the, let's go PlayStation 3 and Xbox, so it was Xbox 360. Yeah, thank you. Those days, all Xbox 360s use the same equipment. All PlayStation 3s use the same equipment. So when they designed a game, they could optimize it for that exact platform, exact timings, exact graphics. Now you have like a pro version of the PlayStation, and so they have ones that have better hardware in them. So you really can't optimize perfectly for that now. But if we roll back and say, if you're writing a video game for the Xbox 360, you know that everybody playing this game is playing it on the identical hardware. So potentially in that situation, I'm not saying that's what they did, because we've been past this idea of busy wait loops for a long time now, but potentially they could rely on how long a for loop takes to run on an Xbox 360, because it should take the same amount of time to run on every Xbox 360-ish, given that it still needs to get scheduled by the operating system, and it's possible it might be slightly off based on when it gets CPU time, but it should be at least roughly the same. But now typically when we write software, we want to write it with the understanding that we don't have control over the hardware that's going to be running this. So this concept of saying, oh, I'm just going to do something 10,000 times, and by the time it's done, that's a big enough delay. That makes sense? So even though we saw this work, where we just said, look, main thread, sit here and spin until you're back down to an active count of 1. Even though that worked, probably isn't great programming practice. All right, let's go back to our code here. We can grab the current thread. So inside of any of those threads, they can get access to themselves, including the main thread. We can get the ID of our threads. We'll see that each one has like a unique scheduled ID inside the operating system. We can get a thread's priority and see how the operating system is actually scheduling it. We can get its state. We can interrupt a thread. We can join a thread. So this waits for this thread to die. So if we join a thread, So notice we have two different versions of join. We actually have three different versions of join. One just says, look, I'm going to join a thread and I'm going to wait until you're dead. So with that in mind, I can come in here and I can get rid of this busy wait loop here. And I can say WB1 join, WB2 join, and WB3 join. Now we probably need to try catch these. Yeah. So interrupted exception, we can add a throws. So we can try to do all this. And then catch the exception E. Actually, we could just say print stack trace. Okay, because technically something bad can happen when we try to join a thread. So it throws an exception. So we're going to try to join these threads. Presumably we'll be able to join them successfully. And that will cause these lines to block. Now we could say, well, since WB1 was created first, maybe I could just join WB1. And maybe by the time WB1 is done, actually I could say I can join WB3. And when WB3 is finally done, hopefully that also means that WB1 and WB2 is done. But there isn't a promise of that because of how they're scheduled. Okay, so if I do that, let's see if hopefully at the beginning of the woots, I actually have a couple of intersected stuff. I mean, this might have worked just out of luck because of how the scheduling worked. Nope, it didn't. So see, so I waited only for the last thread I started to finish, but notice that it was finished before WB1 was finished. Man, WB1 really had some bad luck here. Yeah, WB3 finished way earlier. So just luck of the draw from scheduling. So see how that's working? So I really can't rely on the last thread I started being the first one that ended. In this case, they're all doing the same thing. But I can say, I'm going to wait on all of those guys. So rather than doing a busy wait loop, we're just going to say, I'm going to wait on these threads. However Java implements that behind the scenes, not our problem. I'm going to say I'm going to wait on all these threads. Now I go and run it. We should have all our woots last now. That makes sense? So this allows us to wait for a thread to finish. All right. So now there's two other versions of this. We have a join that takes in a number of milliseconds, and then we have a join that takes in a millisecond and a number of nanoseconds, if you want to get really precise, where we can say, you know what, I want to join a thread, but I want to limit how long I'm willing to wait. Because depending on the program that you're doing, you might say, okay, I'm going to wait for a reasonable amount of time for something to finish, but if it's not done, I need to move on. I need to go do something else. And that we can relate to that in real life, correct? You know, you ask somebody to go do something and you say, okay, I'll wait here. And after 5 minutes, you might say, okay, I can't wait any longer. I need to move on. So maybe you decide you're going to go do it yourself, or you're going to ask somebody else to do it, whatever it is. So they've given us some abilities that allow us to operate like that, where we can say, here's the longest I'm willing to wait versus, look, I'm going to wait till you're done. Realistically, most of the problems we're going to solve are probably going to just use the default that I know this thread will execute until it's done. I need to wait until it's done. We need to wait for our ingredients to be complete, as well as our preheating to be completed before I can put the lasagna into the oven, right? So both of those threads would need to complete. and then we could go and actually insert it into the oven. All right, we already saw the run method. This is where all the magic goes. There is this thing called set daemon, which so daemons are kind of server processes that run behind the scenes. They get a little bit lower priority typically on the operating system. So this might be something where you say, you know, I'm going to write a Java program and I want something to happen behind the scenes, but it doesn't really need to be high priority, but I want it to be always worked on when it can be. So then you can set it up as a daemon. We can set the priority to make it a higher priority if we want. That hopefully means it'll get more time. We can even do this within our threads. We can say, okay, I'm going to create 3 or 4 threads, and I want one of these threads to be the highest priority. The other ones could be daemons, or they could be a lower priority, because one of them really needs to get done first. The other one just kind of needs to do its thing. We can tell a thread to just go to sleep for some amount of time. You know, maybe tell it to pause for 3 seconds or something like that. So if we can go in here and we can tell our worker bees to, you know, between each loop through there, wait a second, wait a quarter of a second, and then we'll see it take a lot longer for 1,000 things to come out, right? Because now you have 1,000 things, and if it's a second wait between them, you're gonna have to wait 1,000 seconds for each of those threads to finish. There's 3 threads, so you have to wait 3,000 seconds for it to finish. So that program will take some time. We saw what start did. Okay, so we kind of see what threads can do now. Have a decent idea? All right, so for our homework, fill an array with random numbers and perform a merge sort on that array like we previously did. So this is the merge sort we have in the notes and that we wrote before the last homework assignment. Okay, so this is just merge sort on numbers. Modify this to have the top, see, have the individual calls to merge sort happen inside of a thread. This should be allowed since all parts of merge sort can be done at the same time with only the merge step having to wait for the 2 halves to finish. So hint, you will need to wait for the 2 merge sort threads to finish before you can call merge. That makes sense? All right, so we're going to see merge sort in its where it shines, where it can run on multiple processors. Okay, so you actually already have most of this code. What you're doing is you're now moving pieces of this code into threads and leaving other pieces outside of threads. So probably your merge sort code is going to go in a thread. Your merge code won't, because merge is going to happen. Well, your merge can happen. You're just going to have to wait for it. You could potentially put that in a thread if you wanted to. You just have to make sure you don't start merging until after the previous 2 merge sorts have finished. Make sense? Okay. I will put my current code on GitHub. It'll be called CSC250 threads. And I'll make it public. So you'll have my code from class today, and then I will see everybody on Tuesday.
Also, the hackathon is on Saturday.
Oh, hackathon Saturday, and when do they need to? They need to be signed up like as soon as possible, right?
Yeah, like we're saying 8 p.m. on Friday.
Okay, so there's already notes for this up on Slack, but the hackathon is this coming Saturday, and you need to sign up. I'm going to say as soon as possible. Don't wait till Friday night to sign up so they can help make teams and stuff. This is a really good experience to do these hackathons. You get a lot of practice outside of class. So strongly encourage you to take advantage of this. There's information about it up on Slack in multiple channels. I linked it in all my channels. It's also in general. All right. I will see everybody on Tuesday.